Welcome everyone to this webinar on printing parts first time right. As Jay said, my name is Ashley Eckhoff. Excited to be here today to talk with you about some of the issues we see companies struggling with when they're trying to print parts, and how our Siemens solutions might help with. So let's begin by talking a bit more about the problems that companies face when they're adopting additive manufacturing. So companies producing parts using additive face challenges across the digital thread, and these organizations have questions sort of every step along the way. So they need to understand things like, how do they assess designs for printability? How do they avoid print failures? How do they mitigate issues during production? And then, of course, all these questions feed into their ability to produce quality parts on time and at scale. Now, it's worth noting that I'm going to spend the bulk of this session talking about metal printing, but many of the failures that I will show also happen with plastic printing. The big difference here is in the cost of the failure. So a failed plastic print, of course, may cost, a couple hundreds of dollars, where a failed metal print can often run into the tens of thousands of dollars. So I'm going to spend my time today concentrating on metal printing, mainly because the magnitude of the penalty for failure is so much higher there. But you can know that the problems we're discussing here are many times not specific to metal. So there are many different ways that a print can go wrong, from major failures like a recoder collision that you see in the middle at the top there, to microscopic defects within the structure of the part, which you see down in the lower right. Each of these issues that you see here can manifest in different ways, from parts that are outside of tolerance due to distortions, to surface finishes that are subpar, to actual part failures in the field due to structural weaknesses. And each of the problems that you see here basically equates to money and time that's lost. Now, how your company approaches these problems will often differ depending on where you are in your knowledge acquisition journey for additive manufacturing. So we can portray a company or a worker's position in the journey by using some common terms that we normally use for job experience. So I've separated these into three levels. We have the apprentice level user, which they've got frequent build failures, and first article parts are failing more than maybe 40% of the time. They often attempt to use varying support strategies to solve these build failures, but that's usually a sort of inefficient process, and they don't always have the experience they need to guide them in that. The journeyman has less frequent first article build failures, but they're still experiencing 30 to 40% failure rates when building a part or a group of parts for the first time. They're more advanced, trying to nest multiple geometries together. They're concerned about things like surface quality and post-processing management, but they're still largely probably using supports to try and fix build problems. But they may occasionally also try to adjust the orientation, especially rotating things around the Z direction, to attempt to alleviate major problems like recoder collisions. So the master additive engineer is using simulation to tune the different process parameters. They're trying to solve issues like shrink lines, distortion, and porosity, and their first article failure rates are usually somewhere less than 20%. They understand the additive process for their hardware, and they're able to drive a much higher return on investment for their processes. So here's the problem. Moving up this learning curve organically in a traditional fashion takes a lot of investment and a lot of time. So therefore, successful companies are always looking for a way to short-circuit that process and jump ahead in their experience level with a minimal investment in money and time. So this is where software comes into play. Applying the right software according to your experience level and need can augment the natural knowledge acquisition process, allowing for a much faster path and an improved return on investment from additive. So if we talk about the costs, everyone knows about the upfront costs for additive manufacturing. So these are the costs of acquiring the machinery, the cost of the materials necessary to print, but there are also other hidden costs that are not discussed as often. So here we have hidden production costs, and these also contribute to the cost of knowledge acquisition. So for example, even with a failure rate below 20% at the master level, we're still talking about as many as possibly 1 in 5 prints failing. And those material and time costs must be factored into the cost of the part provided to the customer. And what we haven't talked about is how trial prints and testing can also be an ongoing cost. So when a company acquires a new machine or begins supporting a new material, that often means that multiple rounds of testing are introduced into their process. Now, some companies try to reduce this particular cost by strictly limiting the number of technologies and materials they support. They'll limit the scale of their business. So, for example, if you only do selective laser sintering with titanium, you can't service a customer who needs a part in aluminum. That's business that you can't capitalize on and business for which your competition might capitalize. So, of course, these problems are even worse at the lower levels of AM knowledge, where the failure rates are higher and where companies regularly need to print multiple versions of a part before they get output of an acceptable quality. At these knowledge levels, rarely does unknown geometry print perfectly the first time. So then there are the hidden business costs of acquiring knowledge and training your talent. So these are the other costs that are incurred when moving up through the knowledge acquisition journey and up that learning slope. Unfortunately, investing here means that once those people have additive expertise, they become a valuable asset that's then courted by competitors because those companies are trying to acquire the same expertise that you just invested in growing. So you have to worry about what happens when those people are lured away. Do you replace that skill set? Do you have to invest in your new employees all over again just for the process to repeat itself again? So these two are areas where software can help the process. When your software includes tools to help you print parts first time right, you don't need to invest as heavily in acquiring that new knowledge when you acquire a new machine or support a new material. And when that knowledgeable employee leaves or retires, the software is still available for the next employee to use. So the upfront training costs are lower and the risk of brain drain is minimized. So here's the typical process that a company at the apprentice level might use to print their parts. After designing the part, they do the initial build tray setup, they orient the part manually, they design some support structures. These supports are sometimes created with automated software, but often those tools don't have built-in facilities to help solve print problems, so it's quite often as well that the support structures are created manually. And then, of course, they try to print the part, and more often than not, this results in a print failure of one nature or another. And this begins the iteration process, where the model geometry, the orientation, the support structures, the machine parameters are tweaked over and over again until they get a print with acceptable quality. So how does the journeyman improve on this process? So one thing they often do is they introduce simulation into the process. So this is where they simulate the build in an effort to anticipate areas of failure before they try the print and possibly fail. If the journeyman's really on their game, they'll also introduce software at the build tray setup stage to help with orientation and creation of build support structures. So we still have the iteration, but the iteration cycles are reduced and the amount of resources spent on failed prints is reduced. So some of the things that were previously black art and dependent on the experience of the manufacturing team have now been replaced by software, assuming some of that burden. And finally, we have companies that have attained mastery over their production. So these companies perform all the steps of the journeyman companies, but they also add in a stage to optimize material deposition and machine parameters. So again, it's a software-aided process, in this case where the deposition of the actual material is simulated in an effort to optimize the deposition path and the machine parameters, things like laser power and dwell periods. So the result is that our iteration cycles have reduced further, our failure rate is improved even further, and our need for practitioners of the black arts has finally been eliminated or at least highly reduced. So if your company is at the apprentice level, you probably have tools for design. However, if you want to move up the scale to journeyman, Siemens has a tool called Sonata that can help your additive process move to the next level. So Sonata is part of our end-to-end additive solution. It fits within the virtual production area of the AM workflow, so I'll talk about that a little bit again towards the end of our time today. But Sonata is part of a series of companion tools that all work towards allowing Siemens customers to get a first-time right print in an industrialized fashion. So many customers use Sonata as their sole build prep solution, and then they take the output from Sonata directly into their build processor. So NX has a bunch of built-in build processors, and of course we'd recommend using those, but other examples include things like EOS Print and RP Tools. But Sonata is a great tool for feedback on the proper orientation and proper supports, and they can even try simulating their best guess using some of the rapid-fire simulation capabilities within Sonata. So the process for generating optimized output from Sonata is pretty easy, and it's really fast. I'm no expert, and I'm able to do this. And since Sonata in its current form is an online tool, you first upload your parts using a standard file type, and you start a job within the Sonata system. You set up a bunch of optimization options like printer type, the material, the orientation, some constraints and targets and things like that. And the system then optimizes the orientation for the part and generates supports that conform to whatever option settings you've chosen. Finally, you can inspect the results online, and then you can export the build tray with the oriented part and supports for printing. So let's look at this in action. We'll let the video run here behind me, and I'll kind of describe what you're seeing as we go along. But what you're going to see here is just how easy it is to get results from Sonata. The whole process is completed, as I said, within an online web browser. So here we've already uploaded our part geometry, and we're creating a new job. We're going to select a material and a printer from the drop-downs, and we're going to set various options for things like units and layer thickness, the part offset from the build tray, things like that. We can also choose to have our part remeshed if we want more accurate results, and we submit the job. The system takes the part, remeshes it if we selected that option, gets the data ready for the optimization process. We then choose what kind of optimization we'd like to perform. Do we want to optimize for thermal characteristics, for build time, for material usage, maybe even for the amount of required support removal? And then we, in this case, we chose to optimize for thermal characteristics. And once all those options have been set, we can begin submitting the job and receiving the optimization output. So in this video, we chose to interrogate the output for minimum thermal distortion. But using the Sonata system, we can interrogate the results. We can see the optimal part orientation and optimal support structures. We can interrogate the simulation output and ensure that printing at the suggested orientation will result in thermal distortion that's within our parameters. And again, this whole system is secure, it's online, and it's really easy to use with a minimum ramp-up time.